Good morning, welcome to your snow day lecture for thermodynamics. We're going to continue with problem 331. In this problem we have a container which has a given volume and a mass and is filled with R134A. It has an initial temperature of negative 400 Celsius, and then once it's heated up it reaches a pressure of 200 kilopascals. What we need to determine is the final temperature and the initial pressure of the system. Okay, so for the system, what we know is that we have a given mass, which is 10 kilograms. We also know that the fluid that we're dealing with is R134A. We also know that the volume that is provided is equal to 1.348 meter cubed. We also know that the initial temperature is given to be negative 40 Celsius, and the final pressure is going to be equal to 200 kilopascals. What we need to find, it is the initial pressure and the final temperature. Okay, to do this, we're going to assume that we have a constant volume, since it's a rigid container. So then what we're going to use is the idea that since V1 specific volume at first stage is equal to V2. So we're going to calculate it, and in that case it's going to be the total volume divided by the mass that we have. We take those two values, we find that the specific volume is 0.1348 meter cubed kilogram. So we go in to the tables with the following information. So what we're going to have is that in state 1, we're going to have that the T saturated, it's going to be equal to negative 40 Celsius. And then we find the P saturated at that stage. So we're looking at table A11, and it's going to tell us that the pressure at that point is going to be 51 kilopascals. And in that case, what we're going to find out is we're going to find the values of the volume for the saturated liquid and the saturated vapor. Notice that the specific volume for the saturated liquid is going to be 0.0007053 meter cubed kilograms, and the specific volume for the vapor is going to be 0.36064, once again meter cubed per kilograms. And notice that because the value that we have for the specific volume for the quantity is between these 2 points, we could say that the state 1 is a mixture, a saturated mixture, sorry. Okay, so that means that in that particular case, the pressure that we have, the initial pressure, is going to be equal to the saturated pressure. For state 2, the quantities that we know is the value of the pressure and the value of the specific volume, since we're both given. Now, since the system was heated up, what we assume is that it's going to go from a mixture and then most likely into a superheated vapor. To be able to verify that, we're going to go to table A12 and obtain the value of Vg, and that is going to give us 0.099951 meter cubed per kilogram. The value that we got for the specific volume is equal to 0.36, which is significantly higher than Vg, which once again proves our assumption that it's going to be a superheated vapor. At this moment, what we're going to do is we're going to go to table A13. We're going to look for the pressure, which is 0.2 megapascals, and then we're going to look for the value of V in that table. And then we're going to see, to find the temperature, we have to interpolate between 60 and 70. And then the value of the volumes that we have are going to be 0.13206. Then it's going to be 13641, and that one that we're looking for is 0.1348. All of these ones, of course, are going to be in meter cubed per kilograms, and all of these ones are going to be in Celsius. If we do the interpolation, we find that the temperature 2 is going to be equal to 66.3 Celsius. If we plot this process, we're going to see, so we have pressure and we have a specific volume. Once again, we have our little mountain. And notice that we started as a mixture over here. And the only information that we have is that this is constant volume. So it's going to be on a straight vertical line. And it's going to go to the second point. So this is going to be your state 1. And this is going to be your state 2. The next problem in the lecture is problem 3.51. In this problem, there is a piston cylinder device which has a 0.005 meter cube of liquid water and 0.9 meter cubed of water vapor, which are both in equilibrium at 600 kilopascals. The heat is transferred using a constant pressure until the temperature reaches 200 Celsius. We need to determine what is the initial temperature of the water, determine what is the total mass of the water, calculate the final volume, and also show the process in a PV diagram. In this case, what we know, the information of the volume of the liquid, which was equal to 0.005 meter cubed. We also know the volume of the vapor, which is equal to 0.9 meter cubed. It also told us that the pressure is equal to, the initial pressure is equal to 600 kilopascals, and the process remains with constant pressures. Therefore, both of the pressures are going to be equal to 600 kilopascals. Then we have that the final temperature is equal to 200 Celsius. What we need to find, it is going to be the initial temperature. We need to also find the mass, the final volume, and we need to do the PV diagram. So notice that one of the assumptions that we could use is that at the beginning we're given both liquid and vapor. So at the beginning, state 1 is going to be a mixture. Okay, so we'll start. At state 1, we're going to say that T1 is equal to T saturated, since once again we said that it was a saturated mixture, and this is going to be equal at 600 kilopascals. So we go to the table and we find that for this particular pressure, T saturated is going to be 158.83 Celsius. At that particular point, since it is a mixture, we need the value of Vf of the specific volume of the liquid, and that is going to be equal to 0.001101 kilograms per meter cubed, and the specific volume of the vapor is going to be 560 per kilogram. Okay, so if we need to find that what is the amount of the mass for the liquid, we do a ratio between the volume and the specific volume, and the same thing for the amount of the vapor. So for the fluid, we simply take the volume of the fluid divided by the specific volume of the fluid, and this gives us 5.43 kilograms. And we do the same process for the vapor. And then this gives us 2.852 kilograms. And if we added this too, that is going to give us the total mass that we're going to have. And in this case, it's going to give us 7.395 kilograms. Okay, now at state 2, the information that we know is the following. We know that the pressure remains the same, so we know P2 to be also 600 kilopascals. And we also are given a temperature of 200 kilopascals. So what we need to determine is what is going to be the phase of this particular state. If we go to the table A5, we're able to find that for this particular pressure, the temperature that is saturated is going to be equal to 120.21 Celsius. Therefore, we see that the temperature final is greater than T saturated. That means that we're going to be a superheated vapor. If we go back to the table, we're going to see that the value of V2 is going to be equal to 0.35212 meter cube per kilogram. Therefore, to be able to find out what is the final volume, we take the specific volume, a 0.2, and we'll multiply it by the total mass that we found in the previous step. And that is going to give us 2.604 meter cubed. Now, to draw the plot, so we lose pressure in a specific volume. Once again, we got the mountain. We started as a mixture. So this is 0.1. And then that is the process is isobaric. So the pressure is going to be constant, horizontal line. And then we comes out superheated, and it goes into this direction. Continuing with the lecture, the next topic is the ideal gas equation of a state. An equation of a state is simply any type of equation that relates pressure, temperature, and a specific volume for a substance. The easiest version of an equation of a state is the ideal gas law, which we have all seen in chemistry. This is defined as P equal R times T divided by a specific volume. In this case, the R is a gas constant. This gas constant is specific for each gas that you will be using. The values of R are found in table A1 in your textbook. The alternative way of using a specific R for each individual substance is to use a universal R, defined as RU. In order to do that, you simply use RU when you multiply R times capital M, where capital M is the molar mass of the particular gas that you will be using. Once again, that molar mass is found also in table A1. Now, if we define the mass of a gas or a mass of anything to be the molar mass times the mole number, and we simply identified an equation of the state where it has fixed mass, we could simply say that the quantities in first state are going to be equal to the masses on the second state. Therefore, P1, specific volume 1 divided by T1, is going to be equal to the same quantities for state 2. And in this case, you will be able, you have 6 quantities. Once they're giving you 5, you can solve for the 6th one using a simple algebra procedure. There are many ways that you could define the ideal gas law, depending on what information is provided, whether you have volume or you have a specific volume, whether you have the universal constant or whether you have the ideal constant for each particular gas. These are some of the variations that you will use that we see. Also notice that there are specific ones that have a bar in the top. Those are for molar values rather than for mass values. So let's go over example 3.10. In this example, the gauge pressure of automobile tire is measured to be 210 kilopascals before a trip, and then 220 after the trip. In this location, the pressure is going to be equal to 95 kilopascals. Assuming that the volume of the tire remains constant throughout the trip and the air temperature before the trip was 25 Celsius, we need to determine the air temperature of the tire after the trip. So for this problem, we know that the initial pressure is equal to 210 kilopascals, and then the final pressure is going to be 220, and that at that particular state, the atmospheric pressure is equal to 95 kilopascals. We also know, according to the problem, that the volume is constant and that the air temperature is equal to the air temperature at the beginning is equal to 25 Celsius. What we need to find, it is the temperature 2 of the air, and that's it. Okay, so for us to be able to use ideal gas laws, we always need to be in absolute values, both for pressure and temperature. So the first thing that we're gonna do is calculate T1. to be 25 plus 273, and that is going to give us 298 Kelvin. We do the same process for P1 and P2, in which both of them are going to take the actual value, the gauge value, plus the atmospheric value to make it into absolute values. This is going to give us 305 kilopascals, and P2 is going to give us 315 kilopascals. So one of the assumptions that we're going to do is that there was no leaks on the tire. Therefore, the assumption is that the mass is constant. That indicates that P1, V1, T1 is equal to P2, V2 divided by T2. We also said that the volume is constant, so these two values will cancel out, and once again we have now P1, T1 is equal to P2, T2. Since we're looking for T2, we simply solve that equation. T2 is simply going to be T1 times P2 divided by P1. We do a little bit of algebra and substitute, and we find that the temperature is equal to 307.77 Kelvin, or 34.77 degrees Celsius. So one of the things that we have mentioned in class is that vapor is not the same thing as a gas. And this plot allows us to realize that. For example, this is the plot of temperature and a specific volume for water. As we know, the water, as the temperature increases, is going to become a vapor. So all the area that we have in this part over here is going to be your superheated vapor. As the pressure reduces, notice that you get to this range over here, the red range, and that is going to be your ideal gas. So vapor could become a gas if the conditions are ideal. For example, it means that the pressure has to be very low. Usually, any point after 10 kilopascals, water vapor could be treated as an ideal gas, regardless of the pressure of the temperature in which it is. At higher pressures, you need to be at higher pressures over here, you need to be at very elevated temperatures for you to be able to treat vapor as an ideal gas. So once again, for you to be able to treat vapor as an ideal gas, there have to be conditions that have to be met. We start by the pressure, low pressures, and also high temperatures. They're usually the two requirements that you're going to have for you to be able to try the vapor as an ideal gas. So now let's continue with the compressibility factor. And this is basically a way to evaluate how a gas, whether it should be treated as ideal gas or not. So not all the gases or the real gases are going to be ideal gases. Once again, the ideal gas is kind of like a perfect idealization of how a gas should behave. So what we do is we calculate the compressibility factor. This basically tells you how far away you are from the ideal condition. Now, if the value of Z, which is the compressibility factor, is equal to 1, then you could treat your gas as an ideal gas. However, when it deviates from 1, when it's larger than 1, or when it's significantly lower than 1, then you're going to have significant errors or deviations if you use the ideal gas. Whenever we want to find out the value of Z, or the compressibility factor, we simply take the value of pressure, specific volume, and we divide it by RT. And then notice that this is equal to the ratio of the actual volume divided by the ideal volume that you're going to have. Now, these values are going to be proportional to the level of temperature and the level of pressure that you have, and whether you have a high value of pressure or low value of pressure, and the same thing with the temperature. So now, how do we determine if something is high or low pressure or temperature? That is simply given by the value of the critical temperatures and the critical pressures that you're going to have for your particular gas. Now, if you recall from the beginning of chapter 3, the critical point is defined as the point at which the saturated liquid simply converts to the saturated vapor 100% without going through a saturated mixture process. So to actually obtain the value of the compressibility factor, what we do is we use table 3.47. This table 3.47 uses a reduced pressure and a reduced temperature as the part of the data. The reduced values is simply the value of the quantity that you're using divided by its critical counterpart. For example, PR, which is the reduced pressure, the value of the pressure that you're using divided by its critical pressure. And we do the same definitions for temperature. For volume, we have the actual value divided by the definition of what would have been the volume using the critical values and the ideal gas law equation. So if you notice, that's the ideal gas law. And simply instead of using T and P regularly, we use the critical value for each of them. Now if we look at the table, notice that the horizontal axis is equal to the reduced pressure, and each one of the lines corresponds to a particular reduced temperature. Notice that all of them are fitted for multiple gases, including methane, ethane, propane, and nitrogen. Once you have determined, so for example, let's say you have a particular pressure and a particular temperature, you go across and you find the value of your compressibility factor. This is a generalized compressibility chart, and it's one of the easiest ways to find the value of your compressibility factor. Okay, so let's go over example 3.11. In this example, we have to determine the specific volume of the refrigerant 134A at 1 megapascal and 50 Celsius. We're going to give a couple choices. First, we're going to use the ideal gas equation of a state. Then we're going to use the generalized compressibility chart to find out the value for Z. We're going to compare it to the values obtained in the actual tables, which is given. And then we're going to determine the error involved in each one of the cases. Okay, so for this problem, the information that we know is that we have R134A as a working fluid. We have that the pressure that it has is equal to 1 megapascals. The temperature that it has is equal to 50 Celsius, and that is going to be 323 Kelvin. And what we need to find is the specific volume. Okay, so let's start with choice A, which was the ideal gas. So in this case, the first thing that we need to find is the value of R. And for that, we go to table A1. And then we find that is for this material is 0.8149, and the units are going to be kilojoules, kilograms, Kelvin. We also need to be able to find, for later purposes, the critical value of the temperature, which in this case is 374.2 Kelvin. We also find the critical pressure, which is going to be 4.059 megapascals, and the critical volume, specific volume, 93 meter cube per kilomole. Oops, kilomole. Okay, from the ideal gas, we know that PV is equal to RT. Okay, so if we solve for V, so it's simply RT divided by P. We take the values that we have in the top over here, and that gives us that the specific volume is equal to 26325 meter cube per kilogram. So this is the solution that we're going to have for the ideal gas. Then we're going to, the second choice is the compressibility chart. For that case, first we need to find the reduced pressure, which is equal to the value of the pressure that we have divided by the critical value. So it's going to be 1 megapascal divided by 4.059, and that gives us a reduced temperature pressure of 246. We do the same thing for the value of the temperature, and that is going to give us 0.863. Now we're going to go to the compressibility chart. So using this chart, we first find the value of the reduced pressure. So it's 0.25, so it's somewhere over here in the middle. And then we go up, and notice that the reduced temperature that we have is 0.861. The lowest that we have is 1. So it's going to be somewhere underneath over here. We're going to do an estimation, and we're going to evaluate it to be somewhere in between these values. Your book actually provides a value of 0.84. That's the one that we're going to use. So once again, from the compressibility table, we found that Z to be somewhere close to 0.84. So if we want to correct the value that we got from the ideal quantity, we find V and is equal to the compressibility factor times the ideal value that we found. And that means that we're going to get a value of 0.022113 meter cubed per kilogram. Okay, now we have to calculate the percentage error to the actual value that is provided in the tables. So once again, we have the ideal value, and we got the corrected value using the compressibility. So for A, if we calculate the percentage error, and by percentage error is simply the calculated minus the real divided by the real times 100, we find that for the first part, the error is equal to about 20%, and for B, the error is equal to 1.45%. So notice the difference. Once we use the compressibility factor and we actually do the correction from the ideal value, we reduce the error significantly from 20 to less than 2% of error, which is one of the reasons you always have to use the compressibility factor to double check the approximation whether an ideal value is correct or not. There are other equations of states. Depending on the substances that you're using, there are some equations of state that are more valid for the particular gases that you will be evaluating, the particular fluids that you'll be evaluating. For example, we got the Van der Waals equation of a state. Notice that once again it relates temperature, specific volume, and pressure. But in this case, we have constants A and B, which are functions of the critical value of the temperature and the critical value of the pressure. We also have some other equations of the states. Notice they are a bit more complex, more terms, but once again, the similarity is that they relate pressure, temperature, and a specific volume. Notice also that this particular equations using constants like A0, B0, those constants are found on these tables, and these tables are noticed that are listed the particular constants that you're going to use, and they're done specific for each one of the gases that you treat. There are going to be differences between the equations of states and dependent of the fluid that you're going to be using. For example, when we use the Van der Waals equation, it has only two constants, and it's very accurate of a limited range of both pressure and temperature. Notice that the Beatty-Bridgman has 5 different constants, and is very accurate when the density of the particular gas that you're using is less than 0.8, that the critical value of the density. Then we have the Benedict-Webb-Rubin, which has 8 constants, a lot more, but notice that the value of the accuracy is a lot higher than what we had before. We got the Stowbridge, has 16 constants, and is more suitable for computer applications like fluid dynamics or CFD applications. And the variable may vary the number of applications depending on the number of accuracy that you are going to be using. Notice that in many cases you got plots like this in which you have how the percentage error changes for a particular equation, and in this case is for nitrogen. So once again, the application will be 100% dependent on the properties that you have and the fluid that you will be using. Now let's go over problem 3.84. In this problem, we need to determine the specific volume of a superheated water vapor, which is at a pressure of 3.5 megapascals and a temperature of 450 Celsius. We have to find this specific volume based on the ideal gas equation. Once again, we have to have the compressibility chart, and then we have to do the steam tables. And we need to determine the error for the steam tables, which is the most accurate case compared to the other two cases. Okay, so for this problem, we know that we have a superheated vapor that has a pressure of 3.5 megapascals, and it has a temperature of 450 Celsius. And what we need to find is what is the value of the specific volume. Okay, and then we're gonna do that using the ideal gas law. We're gonna use the correction of the compressibility value Z and the steam tables. Okay, and once again, this is the accurate value, the real value, and then we're gonna compare it based on these two results. So what we're going to do is first we're gonna find the properties of water in this case, and we're gonna go to table R1 to get the values of R. So that's going to be 0.4615 kilojoules per kilogram Kelvin. Then we're going to also find the value of the critical temperature, and that is going to be 647.1 Kelvin, and the critical pressure 22.06 megapascals. So for the ideal gas, we're simply going to find out the specific volume to be RT divided by the value of P. We take the values that we have from the problem. Please remember that once again the temperature has to be converted into Kelvin. So this is equal to 2 to 723 Kelvin. We substitute it into here, and we find that the specific volume is 0.09533 meter cubed per kilogram. Okay, for part B, once again, to use the to calculate the compressibility factor, we need to find that the reduced pressure, which is the value of the pressure divided by the critical. And using these values, we're going to find it to be 1.59. We do the same thing for the reduced temperature, and we find that to be 1.12. Now what we do is we go and look once again to the compressibility chart, and that is going to give us this. We find the value of about 1.59, so this is really close here. And then we go to about 1.2, so we go up here. And notice that it's very close to 1, and you book approximated to be 0.96. So that is the value that we're going to use. So the value for Z, we're going to have it to be 0.961 as the book is provided. If we take the actual value of V, of the specific volume using the compressibility value, we simply take V, Z, times the ideal value. And then using these calculations, we find that the specific volume is 0.9161. Okay, so now we have the one for the ideal, the one using the compressibility factors, and now we're gonna simply go and get the one for the steam tables. For the steam tables, you go to table A6, and for the value of this pressure and this temperature, we find that the value of a specific volume is equal to 0.09196 meter cube per kilogram. And then we see, comparing these two values, the percentage error for part 1 is going to be around 3.7%, and compared for B is 0.4%. So the percentage is not as high in this case for case A, but notice once again, by using the compressibility factor, notice how the percentage error reduces significantly. Once again, remember that the real value or the most accurate value is always going to be from your tables. These two values are approximations. Okay, this concludes chapter 3, which means that now we're ready to take our first exam. Once again, the exam is going to take place the Wednesday after we come back from spring break. It's going to cover chapters 1, 2, and 3. The exam is going to have two components, similar to the ones that we have done in the quizzes. The first component is going to be a theoretical part, in which you're going to have to provide definitions or simply descriptions or theoretical components. And the second part are going to be problems. And once again, they're going to be focused between 1, 2, and 3. In order to be ready for the quiz, please go back and review every single one of the problems that we have done in class, and also the additional problems that were provided on Blackboard. Also, don't forget to complete your online quiz, which is due by midnight tonight. If you have any questions, please feel free to contact me via email. And I hope that this lecture was not terribly bad, and it somehow makes up for us not having the class due to the snow day. Please stay warm and safe. Take care.